Hello viewers, here is Dr. Mala Das Sharma. Welcome you to my tiny YouTube channel MALACHEMPHILIC. Today I am going to start video number 127, which is the 66th episode of Chemical Thermodynamics, where the topic is thermodynamic properties of ideal solution and Raoult's law. So let's start. Now see, this is one pure liquid, say A. Just 1 minute. This is a pure liquid, say I am denoting it by A. This is another pure liquid, B, and both the liquids are completely miscible. And when I mix these two liquids, homogeneous solution of A and B is formed. Of course, solution does not mean that always it will be liquid-liquid. It may be liquid-solid solution, liquid-liquid, liquid vapor, then your solid-solid, solid vapor, etc. Here I am taking the solution of completely miscible liquid. Okay. Now, when this solution is formed, then solid molecules enters between the solvent molecules. Right. So, based on the size and shape of these solute molecules and solvent molecules, whether they are identical or not, and also the interaction energy between the solvent-solvent and solute-solute molecules, the solutions are of three types. We can divide them into, or we can classify them into three types. One is ideal solution, non-ideal solution, and ideally dilute solution. Now, for all types of solution, two things are common. One thing is that free energy of mixing is negative, that means less than 0, or during this solution preparation, any time the free energy decreases. Why? Because solution preparation is a spontaneous process, and in all spontaneous process, free energy decreases. And second criteria is entropy of mixing is positive. That means during solution preparation, entropy increases or it is greater than 0. Okay. Why? Because when you are preparing the solution, you are mixing, here it is two liquids, mixing two liquids. So, number of particles increases. Number of particles increases means the randomness increases. So, entropy also increases. And this is the expression of entropy of mixing minus nr summation of xi ln xi, where xi is the mole fraction of the component, ith component in the solution. Now coming to the thermodynamic criteria. For ideal solution, the first and most important criteria is ideal solution obey Raoult's law at all concentration and temperature. So first we should know what is Raoult's law. According to Raoult's law, in liquid completely miscible solution, the partial vapor pressure of each component in the solution at a given temperature is equal to the mole fraction of the component in the solution multiplied by the vapor pressure of the component in the pure state at the same temperature. What does it mean? See, this is a solution. It's a binary solution of two components A and B. Both are volatile. So, some of the A molecules will vaporize and will present above the solution. Similarly, B molecules also vaporize. Vapors of A and B will present on the top of this liquid solutions, and then this vapor will exert a pressure on the surface of the liquid, which we call the vapor pressure. That means at a particular temperature, maximum pressure exerted by the vapor of any component, that is the partial pressure of that component. Okay, maximum pressure, that means at equilibrium, maximum pressure exerted by any component is the partial vapor pressure of that component. Okay, so according to Raoult's law, partial vapor pressure of any component, here it is component A, that is equal to mole fraction of that component in the solution multiplied by the vapor pressure of the component in the pure state at the same temperature. Similarly, partial vapor pressure of component B will be mole fraction of that component B in the solution multiplied by the vapor pressure of that component B in the pure state at the same temperature. That is Raoult's law, and Raoult's law is obeyed in ideal solution. So, now we will do the derivation of this Raoult's law. same. So Raoult's law, here it is liquid vapor equilibrium. Okay, one liquid phase is there and one vapor phase is there. At equilibrium, this pressure exerted by any component on the surface of the solution, that is the partial vapor pressure of that component. Okay, now the chemical potential of any component, say ith component in the liquid phase, that must be equal to, we know the equation, chemical potential in the standard state plus RT ln Xi. Xi is the mole fraction of that component in the solution. Similarly, chemical potential in the vapor phase, that will be is equal to chemical potential of the component in the vapor phase in the standard condition plus RT ln partial vapor pressure of that component. Now at equilibrium, when the liquid and vapor are in equilibrium, so at equilibrium, what we know that mu I of the liquid phase must be equal to the mu I of the vapor phase. That is the condition for the phase equilibrium. Chemical potential of the component in all the phases should be same. Okay. So what can I write? I can write mu I liquid phase in the standard condition plus RT ln Xi, that is equal to mu I in the vapor phase standard condition plus RT ln partial vapor pressure of the component I. Now, when, in putting one condition, when this Xi, that means the mole fraction is equal to 1, that means pure component, then Pi, partial vapor pressure will be is equal to the vapor pressure of the pure component. Then what can I write? Then I can write that mu I standard condition in the liquid state plus RT ln Xi. Xi is 1. Log 1 is equal to 0. So that is equal to, I can write it as mu I in the vapor phase, of course in the standard condition, plus RT ln, now it is the vapor pressure in the pure state. Say this is my equation number 1 and this is my equation number 2. Right? Now next what we will do? I will do equation 1 minus equation 2. What was my equation 1? Mu I in the liquid state, of course standard condition, plus RT ln Xi minus mu I liquid state standard condition, that is equal to this mu I vapor phase standard condition plus RT ln Pi minus mu I vapor phase in the standard condition minus RT ln P naught, that is in the pure state. So what we are getting? We are getting that here you see this one cancel and here these two are cancelled. So what is left over? Left over is RT ln Xi, that is equal to RT ln Pi minus RT ln P naught. Okay, so I can write ln Xi is equal to RT get cancelled, ln Pi by P naught, because log A minus log B is equal to log A by B. So I can write Xi is equal to Pi by P naught. So from here I can write Pi is equal to Xi into P naught. This is Raoult's law. Partial vapor pressure of any component is equal to mole fraction of that component in the solution multiplied by the vapor pressure of the component in the pure state. Okay. Now, for ideal solution criteria, first criteria already I told you, ideal solution obey Raoult's law at all concentration and temperature. Second one, that also I told you, that for preparation of ideal solution, that solute molecules and solvent molecules should have the same size, almost same size and identical shape. And next point, the intermolecular forces between these, see here it is intermolecular forces between the solvent molecules and between the solute-solute molecules must be same as that of the solute-solvent molecules. Okay. Now, solute and solvent molecules possess the same tendency to escape into the vapor phase, whether it is surrounded by the molecule of its own type or different, because these intermolecular forces of attractions are same between the solute and solvent molecule. So, its escaping tendency is same whether it is surrounded by solvent molecules, that means different molecules, or surrounded by solute molecules, that means by the same molecules. Next point is enthalpy of mixing is 0. That means during the preparation of ideal solution, there is no heat is evolved or heat is absorbed. Why? Here also what happened when solute molecules enter into the solvent molecules, in the space between the solvent molecules, what happened? It replaces the solvent molecules. So, solvent-solvent interaction or solvent-solvent attraction must be broken. For that, energy is required. And when the solute-solvent interactions are developed, then energy is released. So, the energy required to break the solvent-solvent interaction is exactly same as that of energy released during the formation of solute-solvent interaction. So, net result is no energy change. So, no heat is evolved or absorbed. So, delta H mixing is equal to 0. Similarly, delta V mixing, that means there is no volume change during the preparation of ideal solution. That means the total volume of the ideal solution is the sum of the volume of the component solution. Here also the reason is same, because as this interaction between the solute-solvent is identical of solvent-solvent, so as these solute molecules are same way attracted by the solvent molecules, they should be placed in the same position of the solvent molecules, which is replaced by the solute molecules. Okay, as they are placed in the same position, they are not little closer, means solute-solvent molecules are not little closer than solvent-solvent molecules or little away than the solvent-solvent molecules. So, there is no volume change. Then, the chemical potential of each component of the ideal solution is given by mu y is equal to mu y in the standard state plus RT ln xi. And here already I told you the standard state is the pure state or the pure liquid at the same temperature and pressure of the solution. Now coming to the vapor pressure composition curve of the ideal solution. This side vapor pressure, this side composition of the solution. Extreme left you see XA, that is mole fraction of A is 1, that means it is pure liquid A, and mole fraction of B is increasing this direction. So when B is added to A, liquid B is added to liquid B, the solution is forming, and this line indicates the partial vapor pressure of B. And extreme right, mole fraction of B is 1, so it is pure liquid B, and the mole fraction of A increases this direction. That means when A is added, solution is forming. So this line indicates the partial vapor pressure of the component A, and this line indicates the vapor pressure, total vapor pressure on the solution, which is the sum of partial vapor pressure of component A and component B. So, total vapor pressure is equal to PA plus PB. Okay. Now, it follows Raoult's law because ideal solution. So, PA we can write XA into P naught A plus it is XB into P naught B. So, here what I can write? P naught A 1 minus XB we can write because total mole fraction should be equal to 1 plus XB into P naught B. So, this is equal to P naught A minus P naught A XB plus P naught B XB. So, here it is, I can write P total also, I can write P naught A plus XB into P naught B minus P naught A. This expression also we can write. Okay. Now coming to some examples of this ideal solution. Perfectly ideal solutions are there, but some solutions are nearly ideal in their behavior. And the solution falls into this category are benzene, toluene. As I told you, they have the same polarity, same nature, and same polarity and same size, almost same size. So benzene, toluene, N-hexane, N-heptane, chlorobenzene, bromobenzene, ethyl bromide, ethyl iodide, N-butyl chloride, N-butyl bromide, and most of the dilute solution behaves as ideal solution. Now finally, that according to thermodynamic definition of ideal solution is ideal when all the component or every component in the solution obeys the equation mu I is equal to mu I star plus RT ln xi. That means chemical potential of every component is given by chemical potential in the standard state plus RT ln xi. That xi is the mole fraction in the solution for all composition and for a large range of temperature and pressure. So, hope you have understood this ideal solution criteria. Thank you.